All right, great. Thanks everybody for coming. Today I'll present my dissertation, Snow Atmosphere Exchange in Complex Terrain, and hopefully I will illuminate snow sublimation and snowmelt processes for all of you. Thanks to my committee, Jessica and Dale, who are here in person, and Alex, Michelle, and Ellie, who are joining remotely. Complex terrain means mountains. I'll use both terms interchangeably, but for whatever reason, scientists decided to use the term complex terrain instead of mountains, so I've assumed that as well. So here's the outline of my presentation. I'm going to take you hopefully on a journey to the top of Gothic Mountain, and Gothic Mountain will appear throughout the presentation. I'll start telling you about why we care about snow sublimation, and snow melt. I'll tell you how and where we measure these things. In chapter 1, I'll talk about how much sublimation occurs and how certain we can be about our measurements. In chapter 2, I'll talk about why models can't do a good job estimating sublimation in mountains. And in chapter 3, I'll talk about how we can improve estimates of snowmelt at the end of the snow season. And finally, we'll get to the end of our journey. We'll look back at all the work, and we'll ask who cares. Alpine snow is a key source of fresh water across the globe. This is showing snow cover in a typical year, and you can see that most of the northern hemisphere becomes covered with snow for a good portion of the year. In the USA, alpine snow is also a key source of fresh water. In the upper Colorado River Basin, high elevation snowpack contributes to 70% of the annual runoff of the Colorado River. And that river supplies water to 40 million inhabitants, as well as a $2 billion agricultural industry. And I'll draw your attention to these high elevation areas on the edges of the basin where most of the snow falls. So to predict and track snow or snow water, we track a snow mass balance. And we use this term called SWE, the snow water equivalent, which is how much water is actually in the snow if you were to melt it all. So the snow mass balance, or the amount of snow we have as it changes in time, is equal to the inputs minus the outputs. Inputs include precipitation, redistribution, that's when wind picks up snow, blows it around, it might redeposit it behind obstructions here, or it might erode it like it did around this cabin. And then snow is also lost through snow sublimation, and that's the direct transition of solid ice to water vapor, like dry ice that you might use to create fog. And also, obviously, through snowmelt. To predict snowmelt, we use a snow energy balance. So similar to that bucket of snow mass, we can think about the bucket of snow energy. And energy is used to melt the snow. And the energy available for that snowmelt is equal to a couple different terms, which are written in this diagram. We have the net radiation provides energy to the snow. That's the sum of the incoming and outgoing long wave radiation, that's thermal radiation, and also the incoming and outgoing shortwave radiation, which is solar radiation. There's also sublimation, which affects the snow energy balance. When you remove water vapor from a solid, that actually takes energy away from the snow. And if you were to deposit water, like on morning dew, that would provide energy to the snow. There's sensible heat flux. That's the exchange of heat between the atmosphere and the snow surface. So if the atmosphere is warmer than the snow, that will actually provide energy to the snow. And then it also takes energy to change the temperature of the snow. And in this dissertation, I'll focus mostly on these two terms here, the sublimation term, also known as water vapor flux or latent heat flux, and the sensible heat flux. And these both represent the exchange of water vapor and heat between the snow and the atmosphere. And those exchanges are facilitated by turbulence in the atmosphere. And that's why that presentation is called Snow Atmosphere Exchange in Complex Terrain. We're talking about these two terms. So, like I said, near surface fluxes, or the exchange of water vapor and sensible heat between the snow and the atmosphere, are controlled by turbulence. Turbulence is created when wind blows along the surface. There's friction along that surface, and you get a turbulent flow, which mixes the air up and down. And now we'll talk about how that turbulence facilitates those exchanges. If you consider a snowpack, the air above the snow will be a little bit more humid than the air further above the snow. And so when you just mix that air up, you'll get a net upward transport of water vapor. And with regards to sensible heat over the snow surface, generally it's going to be colder, and just above that it will be warmer. And so when you mix that up, you get a net downward transport of heat or warmer air molecules. And also note that if there's no snow on the bare ground with soil or bare ground exposed, in the middle of the day, the soil is generally warmer, and so then you'll have an upward flux of heat. So these fluxes can be measured by what's called an eddy covariance system. And I'll use this icon throughout the presentation to indicate we have an eddy covariance system measuring fluxes on a tower. You can also model these fluxes by using what's called the bulk aerodynamic method. And these are essentially gradient laws for those who are familiar. And what you need is a measurement close to the surface and a measurement at some height above, maybe 3 meters is a standard measurement height. And then you can use the difference between those measured temperatures or those measured humidities to estimate the flux, along with the wind speed, U, and a couple other parameters there. So measured and modeled fluxes, particularly of sublimation, vary widely. So measurements in the mid-latitudes, which I'm highlighting here in these blue boxes, those are areas where snow cover is seasonal, meaning it disappears in the summertime. Sublimation has been estimated to remove 1 to 50% of the snowpack, which is a really big range if you're concerned about water resources. If we just consider measurement campaigns that have been done in the United States Rocky Mountains, which is just 3 or 4 measurement campaigns, the measurements have indicated that sublimation removes 10 to 41% of the snow, so that's also quite a big range. Models have a similarly wide range. This map is showing the percent of the snowpack that is lost to sublimation across the western US. And if we focus on the upper Colorado River Basin here, we see that sublimation is estimated to remove 20 to 40% of the snowpack. So why are these measurements, or why are the models, why do the estimates vary so much? So there's a lot of complex processes happening here. You can have surface sublimation. That's the sublimation happening on snow that's just sitting on the ground. But sublimation can also happen when snow particles are picked up and blown around in the air. And this process in particular is very difficult to model. And you can also have issues where the ground cover is heterogeneous, or it's, there's different types of ground cover exposed. So this is a picture in the fall when the snow is patchy. This is a picture in the spring when the snow is patchy. And if you have an eddy covariance system right here, it's going to measure a combination of what's happening over the snow and what's happening over the bare ground. So that can add some difficulty to your interpretations. So why are these fluxes difficult to model? This is what the models can do well. The models are based on theories that were developed over cornfields in Kansas, so really flat, kind of simple terrain. This is a field in Kansas, not sure if it's corn or not, but the wind blows over the surface. Probably not. The wind blows over the surface, you generate turbulence that induces the heat fluxes that we're trying to model, or the water vapor fluxes that we're trying to model, and then we can measure those with the tower. But let me tell you about some assumptions that we have to make for these models to work well. To put these assumptions simply, turbulence should be generated over a flat surface, so that's happening over this field. And the ground is also supposed to be horizontally homogeneous, i.e. all the same surface material, which is pretty much satisfied here with this consistent short grass cover. But let me take you to the real world of Colorado. I guess Kansas is also the real world, but and see if these assumptions apply. So we're going to zoom in to a headwater basin of the Colorado River, right here north of the Gunnison River. And the image is loading slow. There you go. This is the East River Valley at an elevation of about 9,000 feet in the middle of winter. So do we think these assumptions apply here? This is Mount Gothic Mountain, again, in the background. And let me show you another Google image, oblique satellite image. This is Mount Gothic, or Gothic Mountain, excuse me. So is turbulence generated along a flat surface here? Maybe on the valley floor, but we can also have friction and turbulence being generated up high above the valley. And so turbulence is not only generated along a flat surface in this environment. What about the horizontally homogeneous assumption? There's forest cover here, bare ground or soil. And then when the snow becomes patchy, again, we don't really have all the same surface cover. And this is a picture of our field site that I'll talk about shortly. For a lot of these reasons, snow-atmosphere exchange is not well understood, and this is concerning. In 2021, snowpack in the Colorado River Basin was near average, but the summer stream flow was just 30% of the average, and that concerned the 40 million people that rely on the river. And it also had the news media quite excited. And these are all articles from 2021. So that raised the questions, where did the snow water go? And so scientists began to hypothesize, maybe it's sublimation, maybe it's summer evaporation, maybe there's a groundwater process that we're not familiar with. And to answer these questions, in 2021 to 2023, 3 government agencies heavily instrumented the Upper East River Valley, which I've shown pictures of. And these campaigns were together referred to as the S3 campaigns. We at the University of Washington received a grant for the sublimation of snow campaign. And this is the sublimation of snow team out in the field, a bunch of University of Washington people, a couple other organizations, and thank you to NCAR, Earth Observing Laboratory, who helped us set up a bunch of the instruments, if not most of the instruments. So I'll highlight some of the instruments that we'll use. There were 4 flux measurement sites. Wow, yeah, things are loading pretty slow, huh? All right, I'll keep going. I think it's just, well, actually, okay, there you go. 4 flux measurement sites, which are shown with these orange towers. There was a Doppler LiDAR deployed in the center of the valley, which I'll talk about later. And there were many, many other instruments that I don't have time to talk about today. This Kettle Pond site was the site of the sublimation of snow measurements. We had 4 instrumented towers. And as you guys heard earlier, Danny and I, with occasional visitors, spent 2.5 months out in the field digging snow pits. We dug about 46 snow pits, which created a rich data set to accompany all of the automated meteorological data collected. And all of the data that we collected, both by hand and automatically, is publicly available on the NCAR website. So the 3 chapters of my dissertation are each lessons from the S3 campaigns regarding snow processes, snow atmosphere exchange processes. So what did we learn? This is the snowpack snow water equivalent over the 2022 to 2023 winter, and each chapter will tell us about a different process that happened during this winter. So we can see that the snowpack peaked in late April and began to melt at the beginning of May. This is a plot of daily sublimation across the entire winter, and I'll draw your attention to this event in December and this event in April, which were 2 of the 3 highest daily sublimation rates of the season. This is a typical midwinter day with active sublimation happening. This is a spring day with patchy snow where the snowmelt accelerated. So in chapter 1, I'll tell you that blowing snow was responsible for most sublimation that we measured, and that measurements are least certain during blowing snow. Measurements of sublimation are least certain during blowing snow. And I'll talk about this event, December 21 to 22, where we had a bunch of sublimation and a bunch of blowing snow. In chapter 2, I'll talk about valley scale winds and how those valley scale winds are responsible for high sublimation rates in late spring, and models also underestimate sublimation during these events. And I'll highlight this April 18th day, where we had the highest daily sublimation rate of the season. And in chapter 3, I'll switch to a focus on snowmelt, and I'll talk about how a process called horizontal advection, which is not included in most models, increases snowmelt rates, at least at our site, by 2 times. All right, chapter 1. So in chapter 1, we'll answer 2 questions. How much sublimation occurred at our measurement site? And how and why do sublimation measurements vary when you place your instruments at different heights? So I'll go through chapter 1 pretty quickly. The measurements here are from the 4 SOS towers. We'll use 12 different eddy covariance systems to measure sublimation. And I'll also use these blowing snow flux sensors that'll tell us when blowing snow was or was not happening. And those, I'll use those to classify all of the sublimation measurements as either during or not during blowing snow. And I'll tell you about one concept that will help you interpret the results. There's something called a constant flux layer, and this is in the lowest 10 or 20 meters of the atmosphere. And fluxes, like the ones I was talking about earlier, of water vapor or heat. This is a constant flux layer is when these fluxes do not vary with height in the atmosphere. And that means if you put an eddy covariance system above the ground at any height in the constant flux layer, you're going to measure what's happening at the surface. But in some scenarios, there can be what's called vertical flux divergence. And this is when fluxes vary with height. And it means that if you place your instrument at different heights above the surface, you're going to get a different answer about the flux. So with that in mind, let's check out our results. This plot is showing the total seasonal sublimation measured by 12 eddy covariance systems at the Kettle Pond site. On the y-axis, we're looking at height of the instrument above the ground. On the x-axis, we're looking at the sublimation as a percent of the seasonal maximum snowpack. So from our instruments, we can see that the snow lost between 5 and 10% of the snowpack to sublimation. Previous estimates in the Rocky Mountains using single eddy covariances measured between 10 and 40%, but our estimates at this site said 10% of the snowpack was lost. And we can also see that there's quite a bit of variation with height. So I've now taken those same measurements and split them into two categories, during blowing snow on the left and not during blowing snow on the right. And what we see here is that during blowing snow, the flux measurements increase with height up to about 10 meters. And not during blowing snow, they're pretty constant with height, and they're all within plus or minus 20% of each other, which is a standard estimate of uncertainty for these measurements, while they're not within plus or minus 20% of each other here. And let me show you one more plot like this. This is during the the December 21 to December 22 blowing snow event. This is an image taken from a webcam on one of our towers. This image is at 5 p.m. This image is an hour later. And so you can just see that the blowing snow was completely obscuring the view of the camera. And during this event, we see that there was a massive difference between the lowest eddy covariance system and the 10-meter eddy covariance system. During this event, 10-meter measurements measured 4 times more sublimation than 2-meter measurements. So we hypothesize that the reason we're seeing this vertical flux divergence, this increase in sublimation with height, is because there's blowing snow sublimating in the air, adding water vapor. And so you measure surface sublimation when you're closer to the ground, and as you get higher in the atmosphere, you're adding, or excuse me, you can also measure additional contributions by blowing snow sublimation. So in summary, we asked in chapter 1 how much sublimation occurs in the headwater basin of the upper Colorado River. And we found at our site that 10% of the seasonal maximum snowpack was lost to sublimation if we use the 10-meter measurement. And then we found that measurements vary primarily in the vertical direction due to blowing snow. And what are the impacts of this? On a seasonal level, the 10-meter instrument measured 20 to 50% more sublimation than the lower instruments. And those lower instruments at 2 to 3 meters, those are the standard deployment height for these measurement systems. During one event, a 10-meter instrument measured 400% more sublimation than the 2 to 3 meter system. And blowing snow accounted for most of the sublimation during the season, and also this third highest daily sublimation rate. This work was published in October in the Journal of Hydrometeorology with great help from all of the co-authors listed here. All right, so chapter 2. We're moving into the springtime. It's sunnier. There's less snow blowing around because the snow is a little wetter. We'll answer the questions, how do valley scale winds influence near surface fluxes and our ability to predict sublimation? And we'll focus for much of this chapter on this day, April 18th, which had the single highest daily sublimation rate of the season. And this is a picture from April 18th, by the way. So we found in chapter 1 at Kettle Ponds that 10% of the snowpack was lost, but that's one location in one valley. To scale up to the scale of, say, the Colorado River Basin, we need models. But as I discussed in the introduction, models may not do a great job estimating these fluxes in complex terrain. There's this assumption that turbulence is generated along a flat surface, like we talked about. But in this basin, we know that those assumptions are not necessarily met. So I'll draw your attention to this wind that's blowing over the ridge and creating some sort of turbulent regime behind the ridge. These types of interactions are well known. This is a picture of what's called a mountain wave forming behind a mountain. If you live in Seattle, you're probably familiar with the lenticular clouds that can form above or in the lee of Mount Rainier. So we know that these interactions occur. These are well studied. And we also know that these interactions high above the surface could influence the fluxes, say, in this little meadow here. But the interactions between the upper atmosphere and the near surface are rarely observed because of the intensive observations that are necessary, right? You need radars or LiDAR devices, some sort of instruments to measure the upper atmosphere air, as well as surface towers. And a few campaigns, including the S3 campaigns, provide these type of measurements necessary to explore these phenomenon. So to motivate this chapter further, I'll show you some initial results. So here on the x-axis is time, 24 hours in a day, on April 9th and April 18th. And we're looking at the measured sublimation rate with solid lines and the modeled sublimation rate in the dashed lines. We modeled the sublimation using the bulk aerodynamic method that I talked about earlier, and we measured the sublimation using the eddy covariance devices. There's no blowing snow during these days. On both of these days, the near surface wind speeds and air temperatures were quite similar. So what is different about these 2 days? Why is there more sublimation happening on April 18th? If we look to the upper atmosphere, or what are called the synoptic winds, those are the winds high above the surface, we saw that on April 18th, in orange, the winds were oriented blowing across the ridge, while on April 9th, the winds were oriented in the along valley direction. So I'm now going to show modeled and measured sublimation rates across the entire 2022 to 2023 winter season, split into two categories, during cross valley winds and during along valley winds. And so all of the sublimation measurements during cross valley winds were underpredicted, not all of them, but most of them on average were underpredicted by the model. But during along valley winds, the model does a pretty good job on average. So what measurements will we use in this chapter? We're going to use the eddy covariance systems that we've already talked about at Kettle Ponds. We'll also use a measurement from a weather balloon, and this will give us a vertical profile of humidity from the floor of the valley all the way up to high above the ridges. And we're also going to use an instrument called the Doppler LiDAR. So this Doppler LiDAR can do a lot of different things, but one of the scan patterns that it can collect is called the RHI scan, and it goes like this across the sky. And that creates this 2D plane, which gives us a view of the winds in the atmosphere, a vertical slice of the winds. And it measures what are called radial velocities, and I'll walk you through what radial velocity means in a moment. This is a picture of the Doppler LiDAR during a snowstorm. All right, so let's check out one of these scans, and I'm going to zoom into this little orange panel here. And these are radial velocities. And we'll come back to this in a sec. But a radial velocity is in a long beam velocity. I'm going to give it a second to load. So the Doppler LiDAR is placed here in the center of the valley, and it shoots a beam into the sky. It hits a little happy aerosol particle in the air, and then the beam is reflected back to the Doppler LiDAR. And the measurement that it takes is the velocity along this beam. So it doesn't give us a perfect view of what's happening in the atmosphere, but it gives us an idea. So let's go see how we can interpret these radial velocities in this image. The radial velocities are indicated by color. Greens and blues are negative radial velocities, which are towards the Doppler LiDAR. And yellow, reds, and purples are away from the Doppler LiDAR. So along this beam, we see that there's some flow in this direction, maybe upslope flow along the slope of Gothic Mountain. Above Gothic Mountain, we see these velocities towards the Doppler LiDAR, which are not, it doesn't say that the atmosphere is flowing towards the Doppler LiDAR. It mostly indicates that the wind is from the west here flowing across the valley, like we talked about earlier. And then we can see this closely spaced velocity couplet or velocity dipole here, where we have a little bit of velocity going away from the Doppler LiDAR right next to a velocity going right towards the Doppler LiDAR. And maybe we see another one of those dipoles or couplets here. So to help interpret these Doppler LiDAR scans even further, I'm now going to show a simulation of flow across Gothic Mountain. And this simulation is in the same plane that I've been indicating this whole time. Here's Gothic Mountain. And note that this is a highly simplified two-dimensional simulation of flow over Gothic Mountain. And we don't use this simulation more than just to help us interpret those radial velocity scans that I showed a minute ago. So we can see some rotors or vortices or eddies forming behind the lee of Gothic Mountain. And maybe there's some sort of recirculation happening behind the mountain towards the surface. So I'll now take a snapshot of this simulation. And these arrows, which are partially visible, represent the two-dimensional velocity field. And we're going to simulate one of those Doppler LiDAR scans. So we're now going to show the radial velocities that a Doppler LiDAR scan would show you if this was the real atmosphere. And it looks like this. And we can see these velocity couplets that we saw in the real Doppler LiDAR scan show up. And these velocity couplets correspond to those rotors or eddies that we see forming behind Gothic Mountain. And so we use this simulation to note that if you see this velocity couplet, it's likely that you're having a rotor form behind Gothic Mountain. And this is that real Doppler LiDAR scan that we looked up earlier. And so now we have at least some confidence in saying that these velocity couplets that we see are probably a rotor. But again, the simulation is highly simplified, so we won't take it too far. So these rotors here represent a highly turbulent event forming behind the lee of Gothic, which may have some implications for the surface. So let's go and see what's happening on the surface. We're going to use eddy covariance measurements now during the same hour that we collected 4 scans that look very similar to this one. So this is that 20-meter tower at the Kettle Pond site. We'll first look at the vertical velocity, so that's the flow up and down at the 20-meter measurement height. When the blue line is below the black horizontal line, that represents a downward velocity. When it's above the black line, that represents an upward velocity. And I draw your attention in this plot to 2 downdrafts or brief spikes in the negative velocities. And note that this whole time series here is 6 minutes long, so these downdrafts are lasting about a minute long or so. I'm now going to show the vertical velocity at 15 meters. At 15 meters above the ground, we see a similar downdraft, and we also see the downdrafts at 10 meters. If we look at the 3-meter measurement, we don't see that downdraft anymore. That's simply because the flow cannot go into the ground. But what we do see in the near surface velocity is an increase in the variance, which you might know as noise. And that represents an increase in the turbulent energy associated with these downdrafts. So I'll now show you a plot of the humidity from the surface to high above the ridges. So the x-axis here is humidity, and this is height above the surface in kilometers. So here's the top of Gothic. Here's the surface, the valley floor. And we can see it's quite humid near the surface. The humidity rapidly decreases in the first 100 meters above the surface, and then it continues to decrease slowly. And up above the ridges, the humidity is about 60% of the near surface humidity, so quite a bit drier than near the surface. I'll now show near surface humidity measurements. So again, we're measuring these on this tower at the Kettle Pond site. And I've highlighted here the humidities during these downdrafts. So what we see is when we get downdrafts at the surface, the humidity decreases to a lower humidity threshold. And when those downdrafts aren't happening, the humidity slowly increases. So we hypothesize that these downdrafts are carrying upper atmosphere dry wind to the surface. And while we don't have the evidence to show that rotors are carrying that dry air, these events where we have downdrafts carrying dry air to the surface are associated with these highly turbulent events happening at the ridges. And we have additional evidence to support that I don't have time to show today, but happy to show you some of that during the questions if you'd like to see it. But when dry air is brought downwards to the surface, there's then moist air brought upwards, and you can increase your sublimation rates, which we saw earlier. So you get these turbulent events when the winds are oriented in the cross-valley direction. And it's these highly turbulent events that were associated with increased sublimation, which we saw on average when sublimation rates were underestimated by the models. So in chapter 2, we asked, how do valley scale winds influence the near surface fluxes? We found that when large scale winds blow across the valley, large turbulent structures form behind mountain ridges, and they can carry upper atmosphere air towards the surface. These turbulent structures increase the turbulent intensity, the mixing happening at the surface, and they also carry drier air towards the surface, which increases sublimation rates through a process that models don't account for. And so models underestimate sublimation during these events. And these events accounted for the highest daily sublimation rate of the season. This chapter is in preparation for submission to a journal with the great help of these co-authors here. All right, so in chapter 3, we'll shift our focus away from sublimation, and we'll now talk about the other way that snow is lost when it melts. And we'll ask, how does horizontal advection contribute to snowmelt during patchy snow? So first, why do we care about snowmelt? When the snow melts, you get stream flow. This is real stream flow data from the outlet of the Upper East River Valley, and this is real snow depth and temperature data. The temperatures are the colors. The snow depth, as I said earlier, peaked around the beginning of April, and that's also when melt started. And note that when the melt season began, we started to get stream flow. So the timing of snow melt is important for water managers, reservoir operators, et cetera. So we predict snow melt with the snow energy balance, which we talked about earlier. Remember this change in time of the snow temperature term. During the melt season, the snow temperature is approximately constant, and so we can get rid of that term and simplify this down a little bit. And moving forward, we'll use this notation where the snow melt energy is E melt, the net radiation is R net, the water vapor flux is E, that's again sublimation, and the sensible heat flux is H. All right, so let's check out the snow energy balance, what it might look like at Kettle Ponds during a spring patchy snow day. So the net radiation may be a little different on the snow surface and on the ground surface, and models can handle this pretty well. This is not too big a challenge. But for E and H, for the water vapor and sensible heat fluxes, only vertical exchange is modeled in most hydrology and land surface models. But this isn't quite enough because you can develop these large changes in the horizontal direction, right? In the sunshine, the air directly above the soil will be a little warmer, and the air directly above the snow will be cold. And if you remember from earlier, this means that you'll have opposite fluxes of opposite direction right next to each other. And also, what happens when we introduce wind? You'll actually blow this hot air over the snow. And when that happens, you have to account for the horizontal exchange, which again, most land surface models and hydrology models do not account for. So this is showing over bare ground or grass, there's hotter air than the snow. The air blows over the snow and can actually heat it because of this horizontal exchange. When this is happening, your usual measurement methods and modeling methods don't accurately estimate the fluxes of energy into the snow, and you have to take a different approach. And so we'll talk through that approach now. All right, so this is our snow energy balance. The amount of energy it takes to melt the snow is equal to the net radiation plus the water vapor flux into the snow, E, and the sensible heat flux into the snow, H. And trust me when I tell you that these fluxes into the snow are the sum of the fluxes over the bare ground and the advected fluxes horizontally carrying heat from over the bare ground to the snow. So again, the fluxes into the snow patch are equal to the fluxes over bare ground, upwind of the snow patch, plus the advected heat. And that's represented in these equations here. And so we will now substitute these two equations into this common snow energy balance to create our original snow energy balance formulation, which now has these advected terms here and the fluxes over the bare ground here. And again, all we're talking about here is heat that comes out of the bare ground, is blown over, and then gets deposited onto the snow, both water vapor and sensible heat. All right, so how can we estimate these terms? Remember, our goal is to estimate these advected terms. Again, we want to know how large they are because that indicates, how poorly our model's potentially doing when this process is happening. We measured these terms continuously at a 30-minute resolution for the entire season. This term we measured for just 30 minutes throughout the entire season. It's challenging to measure, and we had a unique method for doing so. But because we don't have these two terms measured continuously, we're going to replace them with what we call a residual. And the residual is equal to the two advected terms. And we pop that residual in place of the advected terms. And then we can solve for the residual, which is equal to the remaining terms. So because we measured these four terms continuously, we can then estimate the residual term, which is approximately equal to the two advected terms. And then remember, we measured just this QH for 30 minutes. So we're going to see, how do these compare? How does the residual term compare to the advected heat term? We did not measure the advected water vapor term, but we can make some hypotheses about how large it is based on this result. And so just to summarize, when I show you the results, if the residual is greater than 0, that implies that the advective processes, advection, is providing energy for snowmelt. So we're going to focus on this patchy snow period, which began around May 10th at the site. The first bare ground appeared, and most of the snow had disappeared by 9 days later, May 18th. And I'll focus on this May 17th day in the results. Excuse me. And I'll now talk about how we're measuring all of these terms, right? So we'll estimate the upward sensible heat flux and the upward water vapor flux over bare ground using the eddy covariance system that we've used a bunch already. We will measure net radiation using a couple of different radiometers, one that's pointed at the snow and two that are measuring the incoming long wave and short wave radiation. We're going to measure snowmelt with a LiDAR device. So this device scanned the snow every 5 minutes throughout our measurement period. And when we look at the change in the snow surface, we can estimate how much energy it took to melt the snow. And now for the advected heat, which again, we measured for just 30 minutes. So a couple folks on our team went out to the site in May. It was very muddy. I think it was difficult to look at all the equipment out there. And they set up these polyester sheets on these permanently placed towers, which we buried at the beginning of the season. Know that when they got there, there was actually no snow around the tires. So this is an artificial snow patch. They had to pretty much, carry quite a bit of snow over so that they could replicate this experiment here. So this is a picture showing the IR camera pointed at the polyester sheets. And it will show the temperatures of the polyester sheets, which are made of a specific plastic that rapidly responds to the air. So when you see the temperature of the sheet, that's approximately representing the temperature of the air. So this video is about 30 minutes long, and it shows the air temperature directly above the snow patch. And just know, I'm not going to explain how, but you can estimate the advected heat term with this video. And so here the color bar is on the right. The snow is this black blob at 0 degrees. It's at 0 degrees centigrade because of melting. The air above the snow is quite a bit warmer, between 6 and 14 degrees centigrade. And you can see that there's this small boundary layer forming over the snow patch where the snow is cooling the air. It kind of oscillates with the wind. And with this video, we're going to estimate that QH term, like I said. All right, so results. And this has been highly technical, so I'll remind you again about what our key goal here is. We're wondering how much does horizontal advection contribute to snowmelt? These are satellite images of the Kettle Ponds site, and we'll use these to kind of characterize the conditions at the site. So again, we can see around May 9th, May 10th, snow covered most of the area. And by May 16th, most of the snow was gone. And we don't have a satellite image from the 17th. So we're just going to pretend this image shows the conditions on the 17th when we're actually going to use the rest of our measurements and when they took that video. All right, so I'm now going to show measurements for each term in our energy balance equation one by one. So this plot is showing the energy flux into the snow when it's positive or out of the snow when it's negative. And so we have net radiation first. It follows the daily cycle of the sun. It peaks around midday, and this is representing incoming energy into the snow patch. Next, we have this evaporation term. Remember that this is the evaporation happening over the bare ground. So there was evaporation happening over the bare ground. This is the sensible heat flux upward over bare ground. The ground was losing heat to the atmosphere because it was warmer than the atmosphere. And we're now going to digress to talk about this melt energy term and how we measured that. Remember, we used a LiDAR. It was mounted, well, we had LiDARs on each of these towers, but we used one LiDAR to measure a transect of the snow surface over this red line here. So this red line over the land surface is represented here. The black line is the ground surface. And we can see that on May 17th, the snow surface was this dashed line. It moved down about 5 to 10 centimeters within 24 hours. So this is the new snow surface on May 18th. We take the difference between these lines and then calculate the amount of snow that melted and then estimate the energy it took to melt that snow. And that quantifies this term here. And this is the difference in the snow between the 2 days. Oops. All right, so this is our melt energy term. There was quite a bit of melt in the afternoon. And also note that the melt term was about the same as the net radiation term and peaked a little bit later in the day. So we now calculate that residual term. The residual term is calculated as E melt, or the melt energy minus these remaining terms. And remember, I said that when the residual is greater than 0, more melt occurs than is explained by net radiation. And you can understand that by looking at this equation and noticing if there is a non-zero residual, it means that these terms do not account for the melt energy. And because the residual approximately equals the two advected terms, this positive residual suggests that advected heat does contribute to melt. Okay, so remember, we have that infrared camera for just 30 minutes. So I'm going to show there's just one dot to add to this plot from the infrared camera, and it laid about there. That's when we took the measurements, or our collaborators took the measurements at 12 to 12:30, and it approximately agrees with the residual term. So this infrared camera measurement supports our other results saying that yes, the advected heat is important, and it's approximately as large as net radiation. And know that generally in snow hydrologic models, land surface models, usually only the net radiation is accounted for contributing to snowmelt. And just to explain this process one more time, all we're talking about here is heat that leaves the bare ground. It's warmer than the air over the snow, so you blow this heat over, and it then deposits onto the snow and contributes to snowmelt. So this kind of obvious process in our head, is important. So I'm now going to show a time series of just the residual term. If the residual, again, is greater than 0, we think that advection is important. And here are the satellite images I showed earlier and the residual term. And we can see that on May 13th, the snow cover covered about 62% of the ground area. And the residual term prior and on this day was pretty close to 0. But as soon as that snow-covered area dipped below 50% and snow was really quite patchy, the residual term skyrockets, and it's after the snow becomes this patchy that we start to see advected heat become important. Excuse me. So in chapter 3, we asked how much does horizontal advection contribute to snowmelt during patchy snow? We found at our site that sensible heat advection over patchy snow accounts for approximately 50% of the melt energy. And advection mattered for about 5 days at the Kettle Pond site. And this process, which again is not accounted for by the majority of models, increases snowmelt, the rate of the melt, by a factor of 2. This chapter is also in preparation for submission with the help of these co-authors. All right, so we talked about some highly technical processes. I'm going to try to take it up to a higher level at the very end here. And hopefully you can take some of these messages away. So we use measurements at multiple spatial scales, right? We use tower measurements to find out how sublimation works and to recommend measurement strategies for sublimation campaigns. We used valley scale measurements along with the site scale measurements to improve our understanding about surface fluxes in complex terrain and why models might misunderstand sublimation. or misestimate sublimation. And then we also use this unique high resolution technique to understand horizontal advection as an important snowmelt process. But who cares? We're up here at the end of our journey looking back down at the work, and I think these are maybe the most important questions to answer, maybe more so than all those research questions I posed earlier. So chapter 1 was really motivated by this question about where is the missing water. So our sublimation estimates that 10% of the snowpack was lost to sublimation, that suggests that the process is probably not responsible for significantly declining Colorado River stream flow, as previous authors hypothesized before our field campaign. And so researchers should consider other potential processes, and people in our lab, Danny and Jessica, are already doing this and continuing to do this. But our chapter 1 also made a recommendation to future campaigns that they should consider a higher instrument placement if possible, or at least recognize that you might underestimate sublimation because of blowing snow. There's still some unopened questions. We measured sublimation at this one point in the valley, but we're not sure about sublimation rates on slopes, above forest canopies, at the tops of ridges. All of those are areas where sublimation rates are likely to be higher. So I, for one, am in favor of continuing to measure sublimation. In chapter 2, we found that the models that predict sublimation and other surface fluxes may fail because of interactions between the upper atmosphere and near surface atmosphere. And the broader impacts of this chapter are kind of deep in the literature, and these are improvements that other people have considered, but we recommend that future research consider what are called higher order turbulence closure models that can contribute to turbulent energy budget at the surface. And models should also consider non-local transport models, which have been used for other atmospheric processes, but these models could maybe be used to improve surface fluxes. In chapter 3, we looked at horizontal advection. Previous research did not come to a consensus on whether horizontal advection accelerates snowmelt. It hasn't been measured that much. But our work, which was the first to estimate, at least to our knowledge, the full snowpack energy balance over patchy snow, does suggest that it accelerates snowmelt by up to 2 times. But whether this affects snowmelt timing is not quite clear yet. And I think further work needs to be done here. So does the timing of melt, which can be changed by horizontal advection, does that shift the timing of stream flow forward or backward? And I'd like to highlight that there are some recent model improvements that incorporate horizontal advection. This is kind of the cutting edge for snow hydrology models. And so it's possible to test these hypotheses across larger areas now, and I would be excited to participate in that exercise. So just in addition to these 3 chapters, I've had a couple other contributions. Some of the things I'm most proud of are these published data sets, which were some of those snowpit data, Danny's weather blog. Yeah, these are great. You should use them. And also, there's some open source course material. So if you want to learn more about snow hydrology, we have a great website for that. And thank you to Jessica for all of the opportunities that I was able to, all the connections that I made, all of these co-authors here were because of my participation in the Sublimation of Snow campaign. So thank you to all of the advisors I've had at UW, Dr. Lundquist, Dr. Istanbuloglu, Dr. Horner-Devine, Dr. Friedrich, and thank you to Danny and the UW Mountain Hydro Lab for all the times. And thanks to friends and family as well. All right, thank you.
I have a question. Great talk, Eli. Very interesting stuff.
I think
Just
we've got
curious.
15 minutes or so for public questions. Okay.
General audience, and then general audience will leave, and then Eli's going to do last report. But right now, anybody who's not on this committee, it's very good.
Super cool. Eli, it's been same direction for all this work. Tell me about the methodology for moving like snow crystals and blowing snow from the estimate for water vapor, assumes like the normal IR sensor, right? How does blowing snow affect that? How do you remove that effect? Does it?
Sorry for what?
So
yeah, can you clarify?
So you're separating water vapor from blowing snow, during those blowing snow conditions.
Yes.
Estimating heavy flux
Yeah.
of water vapor.
Mhm.
Does blowing snow ice crystals affect that?
Right. Like, are the sublimation measurements worse during blowing snow? Might that affect our result? Yeah. 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 So Chris asked if the blowing snow can affect the quality of the sublimation measurements, which we were trying to make during blowing snow. So yes, they can affect. And actually, that's been a big challenge for previous campaigns. We were lucky in that the atmosphere is very dry in this basin. And so you don't get a lot of like riming or collection of ice on the sensor. And yes, the particles can disrupt the gas analyzer laser. However, we found that there was only one blowing snow event intense enough to decrease the data quality, and that actually was the December 21 to 22 event that I focused on. So that one event, we had quite a bit of data dropout. But otherwise, at least by the flags provided by the sonic anemometer and gas analyzer, they did not indicate quality issues. Yes, Nicoletta.
Great presentation.
Thank you.
Enjoyed it. You mentioned some physics-based snowmelt models that could include the patchy snowmelt manipulations that you studied.
Yep.
I was wondering if you could elaborate on those models and
Sure.
on the idea that these models are highly parameterized, and if you pile a lot more, is it worth it? And when is it worth it?
Yeah. So I can't speak on well, let me answer the first question, which was how do they work? So these are our measurements of advection over our snow patch with distance into the snow patch. So the amount of advected heat is sensitive, net over a whole snow patch is sensitive to the size of the snow patch. And pretty much what those models do is fit one of these curves. So it's an exponential decay model to estimate the heat that's going into the snow patch based on the snow patch size. And then they apply those to the snow patches of the size based on what that land surface model is modeling. I cannot recall. It was Philip Harder, so it's the Saskatchewan group. I'm not sure. I can't recall, but I will say that they ran an experiment in the Canadian prairies with their model, and they found that the horizontal advection did speed up snow melt in certain areas where the patches were smaller, but they did not find that it moved the total snow melt date significantly.
Question, right? Is it worth
Yeah. Yeah. Yeah, I don't know. Yeah, I mean, it's definitely a good question if it's worth it. I feel like that's the only paper I know where they implemented this bulk method across a large area and answered water resource questions with it. So they said, no, it doesn't really matter, but I feel like maybe one more person should do it.
Something else.
Yeah. I mean, noticing that we saw patchy snow advection mattered for 5 days at Kettle Ponds would further support that it's not that important of a process.
The question online, Drew asked, I noticed most of the models are sort of physics-based models on assumptions. Do you ever use machine learning anymore?
Yeah, I do not use machine learning in my work. I mean, that's definitely a field of research for atmospheric folks. I'm not really sure of land surface of machine learning being applied to land surface and hydrology models. I do remember a statement from my boundary layer meteorology professor who said that boundary layer meteorology, so this part of the atmosphere closest to the surface, is one of the most challenging scientific areas for machine learning because of the sparsity of data. There's just not that many measurements to train these models on. So that's all I can say on machine learning. Thanks, Drew. Yeah, Lynn.
During the accumulation season, I saw you had very small amounts of sublimation. All right, so I would assume that would your instrument have a hard time, while it's actually snowing, to know, you have blowing, physically snowing, but what's being sublimated and what's being deposited?
Right, that's a great question. And actually, part of the time in that December 21 and 22 event, there was precipitation going on. We didn't, like I said earlier, it was fairly dry here, so we didn't have a lot of like instrument issues when it was snowing. But I do think one thing that our data set could be used for would be to examine the amount of snow that's sublimated during precipitation. So like if you have radar estimates of precipitation and that's how you're estimating how much snow you're gaining, that could potentially be incorrect because of sublimation that's happening before it's even deposited. But that's something we haven't explored yet, but I think that would be a really cool study. Right. Yeah. I think that in terms of redistribution of snow, generally people have found that if you're considering the water resources within a single basin, it contains the blowing snow overall on average. Yeah. Thank you, Lynn.
So it strikes me that two things. Could you figure out like what was the tipping point? How much patchiness do you need for it to really start affecting? And the other related question would be like, it seems like what this patchiness does is it doesn't change the melt, it just maybe sharpens the end.
Like on one side of the patch?
Yeah, so all of a sudden, boom, you've lost it all. Does that make sense?
Yes, I do. Oh, I see what you mean. Like the melt rate's accelerating towards the end of the melt season. So for the first question, we don't have measurements of the snow cover every day. We have these satellite measurements every couple days, which is really impressive for 3-meter resolution. This is planet data, which is super cool. But I mean, just using the satellite images we have, we would say that once it crossed that 50% threshold, that's when the snow melt accelerated. There's advection happening during these times, but actually when there's more snow than bare ground, the air over the snow will cool the air over the bare ground. So you have like the opposite effect. You would decrease evaporation during that earlier time. But as far as the drop off at the end of the melt season, I do think that horizontal advection could contribute to that. And I haven't looked at the rates like really specifically, but if you just look at the snow melt, it does seem like it accelerates at the very end of the season. Yeah. 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 So I would agree with that. Steve.
That question. So what's the implication of all of this data and as it relates to what you outlined at the very beginning, the difference between, the amount of snowpack, one day, and how much water went into the Colorado River versus a later time when there was greater snowpack but less water in the Colorado River. What's the implication for your study for that?
Yeah, I think
that's what people always ask me.
Right.
When I say I'm getting a PhD.
I tried to highlight this in the broader impacts, but I mean, I think what we went through was the scientific process, and our measurements may have, ruled out sublimation as a significant loss term. That being said, we only measured it at one site. Sublimation is higher above forest canopies, and it's higher above other ridges or other topographies outside of the valley bottom. But I would say that there's other processes that are happening that are contributing that to declining stream flow. One of the one that's been studied in our lab is the fact that in the springtime, we're getting less snow for reasons I don't understand, but you're getting less precipitation in the spring. And that actually is like a positive feedback because with less precipitation, you have less clouds, evaporation rates and maybe sublimation rates are higher. And so not only are you getting less snow or less rain, but you're also losing more because of the lack of clouds. So I think there's other processes that are being focused on. A lot of people are also studying like deep land surface processes. Yeah, but I would say specifically in this dissertation, we were able to, say sublimation is this 10%, and it might be contributing, but we should definitely focus on some other areas. Yeah, thanks for that question. I think the last one I saw was,
great presentation, right? From my understanding, in chapter 2, turbulence in the wind is created by like when it's going across the valley. But did you also check if the tree or land cover, which is along the valley, like partially breaking the wind and creating like significant turbulence there?
Yeah, that's a great question. See if I have a photo. Around our site, it was pretty sparse. Like there was no forest within about 400 or 500 meters of our site. But certainly other like micro topography is important. I gave a highly simplified version of our conclusions from chapter 2 by showing you these cool rotors and saying, oh, this is the process. But there's other wind processes that are happening in the valley. One of them is that the wind actually rotates So within the valley, you often have winds that are just directly up and down valley, but the synoptic winds will be in a different direction. So simply that rotation in the wind direction can create turbulence that affects the surface. But what we do know is that what's called top-down turbulence is really important in the valley, meaning that any process, maybe due to small hills or forests, like you said, is creating turbulence above the surface, and that can impact the surface. And so it doesn't just have to be the valley winds, but that was like the most concrete example that I could visually show. Yeah, I would like to answer some. Yeah, go ahead.
Dan, welcome to this fantastic presentation. Where can I get a copy of these slides? Also related to advective heat flux estimation, could you comment on the role of snow impurities, for example, dust or soot, in producing patchy snow in the spring that would lead to more advective heat flux, or is that a second order?
Trying to find a picture of the site on that April 18th day, because as people involved in the field campaigns know, there was actually a ton of dust deposited at the site at the beginning of April, and that's why the snow looks dirty. So we know that this dust deposition increased the snow melt rates before the snow became patchy. I don't imagine that the dust would have a significant impact on the distribution of patches across the landscape. If you notice in the picture of the sites, the snow patches are actually generated in like concavities or small divots in the landscape where snow is redistributed throughout the winter. And so that dominates the location of the snow. And I don't have the images here, but we have satellite images from many years that show that the patches at Kettle Ponds actually are in the exact same places year after year. So while I don't think that the dust would influence the distribution of the location of the patches, I do think that they influence the melt. I don't know if the dust was distributed differentially across the landscape, then that would be another method for producing horizontal heterogeneity that could induce advection. That's certainly an interesting topic. But my imagining of the dust is that it's kind of distributed equally across the landscape, and so you might not have a horizontal advection to do that. Thanks for that question, Dan.
You want to do it online? Kabir said, great work, Eli, well done. Sublimation from intercepted snow on canopy can be a significant portion of sublimation. I'm wondering if you have considered that. Could you please comment on it? What are the challenges for repeating these measurements in forested areas?
Yeah, I think that's something that would be interesting to explore more. We did not deploy instruments above the canopy. The challenge there is setting up a tower high enough to get above the forest canopy. I mean, it was expensive for us to set up a 20-meter tower. You might need an even taller tower. That's all I really can say about sublimation above the canopy. But I mean, if we're really trying to nail down this question about processes affecting water resources in the Colorado River Basin, I think we should continue to make measurements just like that. And I'd like to answer this one because it's really important, but Asa Dehan asked if there could be a more limited array of sensors that could provide the same amount of insight for making a long-term measurement network more feasible. Right, because a 10-meter tower is very expensive. I think that what you could do is deploy a blowing snow flux sensor to at least understand when you might be underestimating sublimation, and you could potentially come up with a simple linear fit to these measurements to say, okay, we have blowing snow, we might be underestimating it by this percentage. I think that would be a good approach. And those blowing snow flux sensors, I think, are fairly inexpensive. They're a PVC pipe with a microphone inside, and it just records when you get a particle hitting. So that would be my recommendation there, Asa. Thanks for that question.
Thank you, Eli.
Hi, there we are